Hello, one and all. Welcome to this video, in which we look at an example of Poincare's lemma. So, just a follow-up to the previous video. Now, in thermodynamics and cosmology, entropy is often treated as a state function, meaning that its differential is an exact one form, and I want to show you how that is using this video. Now, to show that the entropy of the universe is both closed and exact, we will analyse its differential form properties in the expanding universe. All right, so just let's restate Poincare's lemma before we look at an example. So Poincare's lemma states that in a sufficiently simple domain, such as Rn, or n-dimensional Euclidean space, or in cosmology that's going to be time plus Euclidean, or any contractible space, every closed form is also exact. Now, closed forms, a differential K form omega is closed if its exterior derivative vanishes, so d omega equals 0. And exact forms, a differential K form omega is exact if there exists a K minus 1 form alpha, such that omega equals d alpha, the exterior derivative of alpha. Now, since the exterior derivative satisfies d squared is 0, so d alpha is 0, every exact form is necessarily closed, i.e. d omega equals d alpha equals 0. However, the converse is not always true. Not every closed form is exact. Okay, and so what we're going to do now, we'll have a look at the example. So let me just close that off a bit. All right, so let's have a look at a setup. So we've got entropy in the expanding universe. So consider a co-moving volume in a homogeneous and isotropic FLRW universe, Friedman, Lemaitre, Robertson, Walker universe. The total entropy S of a cosmic fluid, and in our case we're talking here about radiation, matter, or dark energy, for instance, is going to be given by the following. So this is the total entropy S of some cosmic fluid. Modelled as a fluid, I should say. So S equals U plus PV on T, where U is the internal energy, P is the pressure, V is the co-moving volume, talk about that shortly, and T is the temperature. Now, the first law of thermodynamics states that T ds is equal to du plus P dV. So the internal energy of a system can change due to two contributions, heat transfer and work done. So that's U, the internal energy. All right. We're interested in the entropy, how that's changing according to the internal energy and the co-moving volume, because they're the two main things that's going to affect our entropy. Okay, so heat transfer, delta Q, and work done, delta W. All right, so they're the two things that how the internal energy of a system can change due to those two things. So the du is delta Q minus delta W. So for a quasi-static process, and we're going to be relying on that through this video, where the system remains in approximate equilibrium because it changes only very slowly. So that's one of the assumptions here with this model. We have a quasi-static process. Now this means that every intermediate state, one to another, can be treated as a kind of equilibrium state, where thermodynamic variables like pressure P, volume V, temperature T, and entropy S are well defined. Now, the work done by the system, delta W, is the pressure times the change in volume, P dV. Now, if heat is absorbed, it increases the system's entropy, delta Q is T ds. Thus, we get the fundamental thermodynamic relation that du is T ds minus P dV, because remember, that's really just delta Q minus delta W from up here. Right. Or just you could rewrite that as TDS is du plus P dV. All right, now co-moving. So the co-moving volume element in the expanding universe is given by dV physical, the actual physical dimensions of the volume, is equal to A cubed, scale factor cubed, times the co-moving volume. So dV phys, subscript phys, is a physical volume element which scales with the scale factor A of T. Okay, that's the physical value you would measure. dV com is a co-moving volume element which remains fixed as the universe expands. So in cosmology, the co-moving volume is a measure of volume that remains constant over cosmic time, accounting for the expansion of the universe. It is useful because it allows us to compare regions of the universe at different times without worrying about the stretching of space due to cosmic expansion. So when we talk about co-moving, it's like co-moving distance. You could define the distance between the Andromeda galaxy and the Milky Way galaxy as being one unit, whatever unit you want. You could call that one. Now, for the life of the universe, that will remain one. That co-moving distance will always be one. But the actual physical distance, if you could physically measure it by laying down a measuring rod, instantaneously laying down a measuring rod, you would find that the physical distance grows according to the scale factor A. So the physical distance is the actual measurable real distance. The co-moving distance is a quantity that remains fixed and doesn't change throughout the life of the universe. So the distance between co-moving coordinates between the Andromeda galaxy and, say, the Milky Way galaxy will be one and only one. Right? But the actual physical distance scales with the scale factor A of t. So co-moving volume measures how many co-moving objects, e.g. galaxies, exist in a given region, and it's independent of the cosmic expansion. Right. So since the universe is modeled as an expanding ideal fluid, we express the internal energy as U equals rho times V, where rho is the energy density, and the co-moving volume V expands as V equals A cubed V0, where A is the scale factor and V is some particular initial value, the actual co-moving value. Actually some initial physical value, all right, where A is the scale factor. So differentiating U equals rho V, we get du is V d rho plus rho dV, right, using the product rule there, or Leibniz rule, and then using that dV is d of A cubed V0 up here. We get V0 is constant value times the exterior derivative of A cubed is V0 times 3A squared dA. Now rewrite V in terms of A and divide both sides by A cubed V0. So we do that, dV on V will give us, well, we take all that, divide by V, which is that, and V of course is equal to this, so the V0s will cancel, that A squared will cancel and A squared down here, and we're left with 3 times dA on A, so that's dV on V. Okay, next, so this gives us dV on V is 3 dA on A, which can be rewritten as dV is 3V dA on A. And this means our earlier equation, du equals V d rho plus rho dV, becomes du is V d rho plus rho dV is this object here, and we can replace this dV here with all of this, all right, from up here. We now appeal to the continuity equation in cosmology, which I'll just state here is this here, differential form. One here, or d rho is this object here. Now we're substituting this into du. Okay, we're going to have du is, where are we? This bit here. And where the d rho is here, we're going to put this object here, plus rho 3v dA on A, rho 3v dA on A. And then if we tidy that up, well, what we will notice that 3v rho dA on A will cancel with 3v rho dA on A, and we'll just be left with this pressure term in the middle here. So I'll have minus 3vp dA on A. All right, now applying the first law of thermodynamics, ds is du plus p dv on t, we get ds is minus 3vp dA on A plus p dv on t. And since dv is this object here, 3v dA on A, we can simplify to get ds is this. We're replacing that with this times the p here, so we get this object here. Now, if you notice, well, you can see on the numerator there, the terms cancel each other out, and we're left with ds is 0. So hence, entropy does not change in an adiabatic expansion, meaning ds is 0. So entropy is a closed one form. A differential form omega is closed if the omega equals S. All right, for our result, ds equals 0. Just coming back now, so we have a closed form. But now, what makes a quantity a state variable? Perhaps I should come back and explain that. So a state variable or state function satisfies two key properties: path independence. The value depends only on the current state, not on the process taken. An exact differential, the differential of a state function is the exact one form. Okay, i.e. it can be written as the differential of some function. Now, since entropy is a function of state variables S, V, and T, its differential is closed, meaning the entropy of the universe is a conserved quantity in adiabatic expansion, so ds is 0. Now, adiabatic expansion, I've mentioned those words without defining them, so here we go. Adiabatic expansion is a process in which a system expands without exchanging heat with its surroundings. So delta Q equals 0. This delta Q is not a state variable because it depends on the pathway taken. So delta Q and delta W, change of work, are not state variables. All right, pressure, co-moving volume, temperature, entropy, internal energy are. All right, now this means all changes in the system's internal energy come from work done by or on the system. Since the universe has no external surroundings, its expansion is often approximated as adiabatic. All right. Okay, now just coming back there, as you can see, so it's a process in which the system expands without exchanging heat with its surroundings. Well, the universe doesn't have any surroundings. The universe is everything. So there's no surroundings with which to exchange heat. So it's an adiabatic process, unlike in closed systems that thermodynamics often deals with, where it could exchange heat at the outside surroundings. Now, since the universe has no external surroundings, its expansion is often approximated as adiabatic. Entropy is an exact one form. A one form omega is exact if there exists a function f such that omega equals df. And since ds equals 0, we seek an s, a function s, scalar function s, such that s is a function of the volume and the temperature, the co-moving volume and the temperature. Now, given that s is a function of thermodynamic state variables, it must be integrable, meaning there exists a potential function, i.e. the entropy function itself. Hence, ds is not just closed, but also exact. All right? ds equals 0 is closed, but the existence of a potential function, s, means that it is exact. All right, entropy is a conserved state function in adiabatic expansion, and its differential is an exact one form, meaning entropy exists globally in the thermodynamic phase space. Physical interpretation. So the exactness of ds ensures that the entropy is path independent in reversible thermodynamic processes, and the closedness of ds ensures that entropy is locally conserved in the absence of dissipative effects, like irreversible heat flow or entropy production. Now, in an adiabatic universe, entropy remains constant, but in processes like black hole mergers or Big Bang nucleosynthesis and others, entropy production does occur. All right, we've modelled the expansion of matter as a kind of fluid, and or dark energy as kind of fluid, and some other matters like that. And we've shown that the entropy change is 0, but that's not the case for all processes in the universe. There are many like black hole mergers, Big Bang nucleosynthesis and others, photon decoupling and the others, which do increase the entropy of the universe. So I don't want to give the impression that entropy doesn't change, because I'm not saying that. All right, so for our cosmic fluid, that's radiation, matter or dark energy, entropy in a co-moving volume is conserved. So between any 2 points in that system there, ds, the integral ds, is simply s of a minus s of b is 0. All right, this confirms that entropy is a state function and does not depend on the expansion path. It's just the difference between the 2 endpoints in question. Provided the universe expands adiabatically without entropy production from sources like black holes. Right? So there are sources of entropy reduction in the universe. The net entropy of the universe does increase. Right, conclusion. The entropy of the universe is both closed, S equals 0, and exact. S exists globally as a well-defined function in an adiabatic FLRW universe. The entropy of the universe increases only due to irreversible processes, e.g. black hole mergers, photon decoupling, Big Bang nucleosynthesis, and so on. Now, for ideal cosmic fluids, entropy is conserved in a co-moving volume and does not depend on the details of expansion. The path independence of entropy ensures that we can describe cosmic entropy evolution purely in terms of initial and final conditions. All right, and that's an example of Poincare's lemma. Thank you very much for watching. I hope you find it useful and informative. And if you do, please subscribe and press the like button. And I shall see you all in the next video. Thank you again for watching. Take care, everyone. See you next time. All right, bye.